We've worked it before, so it's not anything new and different. You guys can probably tell me what the symbols stand for, because we did work these prior years in that. So what's C equal? Even know? It's the speed of light in a vacuum, so that means empty space. Nothing interfering with its path. Okay, and basically it's like 2.998. So I'm just going to have you. I always use 3 times 10 to the 8, and that's measured in meters per second. Okay. So then we have wavelength is lambda symbol, and that's wavelength, and it has to be in meters when you use it. So every time you use something that's not, or given something that's not in meters, you have to convert it to meters, okay? So a lot of times wavelengths in the visible spectrum is measured in nanometers. So then we would just divide by 1⁹ to get it in the meters. So every time you're given nanometers, you just divide by 1⁹, and you got meters. So that's just the conversion ratio on that. So V, this is like a V. It looks like a V. It's nu, symbol nu. So lambda and nu. And that symbol represents frequency. And in frequency can be expressed 2 ways. It can be related as hertz, Hz, or it could be seconds to the -1. And that means like per... that's a -1. Okay? So that's, that would be like cycles per second, waves per second. So that's why that second's the only part that you have in frequency. It's like 1/seconds, or seconds to -1. Questions with that? So we'll use this from time to time. If you want to write that down in your notes or something, you can. But we're going to use that. Now, we're going to talk about energy. And energy has relationships with both wavelength and frequency. And so we're going to get into looking at energies of photons and what they are. A photon is just a bundle of energy. It's kind of like a package of energy that's given off by an atom that has absorbed some energy somewhere along the way, whether it's heat or electricity or some other method. And so that's going to introduce us into energy. Usually what you can do, if this is higher frequency, like gamma and X-rays and ultraviolet light, they're higher frequency lights, they're more energy. But if you get down to radio and microwave, they're less energy associated with those type of waves. Okay? So you guys have any questions with that? Higher frequencies is going to be higher energies. Okay? And these are inversely related. One goes up, the other one goes down. Okay? All right, so I'm going to go ahead and have you, in your book, kind of follow along. I want you to turn over to page 254. 254. All right? You guys do that one experiment? Somebody did that one experiment with the forks and the pickle? Anybody do that? We could have did it with the giant pickle.
Oh, yes.
Did it with the brought the giant pickle in and put it up, and then hooked some sort of high energy source to it and shorted out the school and type of thing like that. Plug it in. Okay. Then you have fried pickle. They don't smell very good either. Okay. So this next section gets into talking about Max Planck, and he was a German physicist. And this is on page 254 in your book. And basically what he did was he heated up different solids. And if you put an iron rod or something metal into hot coals and you pull it out, it emits radiation of light, right?
Yeah.
It could be yellow, or the hotter you get it, it could be red, depending how hot you get it. And he found out when that took place, and he looked at it through what's called a spectrum, he got some individual spectrum lines. So if you guys look up there, that chart's up all year long. That's the spectrum chart that gives you line spectrums. So then he found out by doing that, he got off specific lines, spectrum lines, and he found out that they were kind of related as what they call whole number multiples. So there was a specific quantity that was always emitted out, and then he could quantize that, which means it was a specific amount of energy associated with that line, and there were gaps between the spectrum lines that were given off. So that led to this equation, and that equation that we would have would be change of energy is equal to H times V, and this is what we call a quantum of energy when we're looking at that. So they were packets of energy that was given off, and they were specific quantities, and they were called quantum of energy. So I'm going to go ahead and put down here packets of energies. Given off by an atom. Okay, is called a quantum. So the best analogy that I have for this, it's really, really simple. I think it works. I think everybody understands it. That when you go to the vending machine, you got a lot of different things in the vending machine. All right? And you go put your money in the vending machine. Then there's specific money values that you can select from, right? If you got enough money you put in there. Correct?
Yep.
So if I put in my dollar, and I want to get something out that costs 75 cents, I can get it out, right? Okay. But then if I want to go to the next item that gives me more bang for my buck, like a bag of chips or whatever, a little bit more, might cost $1.50. So it takes a step up from that. If I put in $1.25, can I get that $1.50 item? And the answer is no. Okay, unless it's machines, I do this, shake the machine or something like that. Okay, but I can only get out when I put in at least enough energy to get that item out. And that's kind of like a quantum. You have to put in or you get out a specific amount. You have to put in a specific amount of money to get out a specific, something you can eat. So that's kind of what a quantum is. Another analogy, like if you're going up a ladder, okay? You guys, anybody scared of heights in here? You are?
A little bit.
Okay, so let's say you get on this ladder and it's 28 foot, and you got to go to the top. Is that pretty easy to do?
That's easy.
Really? Okay, so as you get up there, what happens to the ladder that each step you take? Starts to wobble a little bit. And then you look down. And you're going, wait a second, I'm getting up here pretty high. If I fall, something bad's going to happen. So I think everybody probably has a concern with heights to a certain point. All right? And so like those rungs of the ladder, they're like certain quantums of energy you need to put in. It could be like steps up the stairways you have to put in. If you don't quite make it to the next one because you're scared, you don't want to get up to that next height because that's getting a little too high for you, then you don't go up any higher. So ladders are like quantums, okay? Specific amounts associated with that. All right? So there's another way I can write this that involves wavelength. So I could write this another way, and we can introduce wavelength in there in our other equations. So change of energy is equal to H times C over wavelength. So if I'm given the wavelength, okay, then I can plug it in. Or if I'm given the frequency, I can plug it in that way. So either way, I can find a change of energy associated with a absorbed or a releasing of energy associated with that. Okay? So I'm just going to look at one problem, okay? And you guys tell me what you think and how I would solve it, okay? So I've got 600 nanometer of light released when lithium is heated. Lithium metal or lithium ions are heated. Okay? What I want to know is I want to know the change of energy that had to take place within the atom in which to... so I just want to know the change in energy associated with that atom that had to be absorbed and released by that atom. So see if you can calculate that for me, okay? So I gave you two equations, right? Make sure you write those down and see if you can calculate what that's going to be. Now, energy is measured in joules. So it will be joules. Joules. Why don't you see if you can do that? This is probably the only problem that we'll do. Then it means it can move up only if it's given enough energy to make that transition. If it's not given enough energy to make that transition, it can't move up. So then it can move up there, it can move up here, if it's given enough energy, it can move up to higher and higher and so on. Okay? Now it doesn't stay there, because all atoms want to do is get to the lowest energy level available. It wants to go back down here. So it doesn't like excited states. It wants to go, it's kind of like us at nighttime when we're winding down and we need to get sleep, to get rested, to get more energy. That's kind of our ground state. And then these excited states would be requiring more energy. So if this electron here that went up to this first level would drop back down, then that energy has to go somewhere, because we have what's called the conservation of energy. Where's the energy going to go? It goes out. And it might go out as a bundle of energy. I'm going to show it as a wave, but it's called a bundle of energy or a photon of energy is what it's called. Okay? And that bundle of energy has a certain frequency. Right? Now this one here, this one that goes up the top, if it comes back down, what kind of energy is it going to have? More or less? More. What's its frequency going to be? Higher. Higher frequencies, higher energy. So it might give off a frequency that we can't even see because it's so much of a high frequency. And those create what we call lines. Spectrum lines is what they produce, spectrum lines. So if we've got a spectrum here that's being produced by these two, let's say that this spectrum would go, down here is red, then it goes orange, yellow, green, blue, violet. Let's say that this one here would be like orange that it would make. So right here we'd have a spectrum line right there that would represent orange. Let's say that this one here is violet. So guess what? It's going to produce one here. Now, there's other ones that are beyond, called UV, that we can't see, and then there's some that's infrared that we can't see. So we could get some off that don't even show up on this spectrum. And so, like hydrogen, it only gives off, I think, 4 visible spectrum lines. So if you guys turn over to page 261, there is hydrogen. Okay? And hydrogen, what do we know about hydrogen compared to the other elements? How many electrons does it have? Only one they have to worry about. What happened is they came up with a way in which to predict these electrons given off. And David Bohr was the individual that kind of did that and was predicting that. And his predictions only really work, and his formula only works with hydrogen. but it was something that they could look at to kind of build off of those type of things. Okay? So that's what's... This light is also sent through a prism, or what's called a diffraction grating, in which to recognize those different line spectrums. Okay. One last thing I want to look at is on page 256, or actually 255. It's called the photoelectric effect. Now, Einstein was given a Nobel Peace Prize, I think, for this. And basically, the photoelectric effect is when certain frequencies of light, when specific frequencies of light shines on metal, electrons are emitted. But it has to be a high enough frequency to do that. So the metals, when you shine a light with different frequencies onto that metal will give up its electrons. And those electrons will be sent out. Okay? That's what the photoelectric effect is. So I'm going to give you 4 little snippets of information about specific things that are going on with these metals and that they're giving off electrons. Okay? 1. Okay? The threshold energy has to be met for electrons to be emitted. If that's not met, there's no electrons that will be emitted. Okay? So it's kind of like, again, it's kind of like if I go to get something out of the vending machine and I have 25 cents, I cannot get something that costs $1 out. I have to put at least $1 in or over $1. So it's called a minimal amount of frequency that has to be added. Any questions on that? Okay, that's the first thing that we need to take a look at. If it doesn't go above it, it doesn't emit, it won't emit any electrons. Okay? So I guess there'll be just 3, because that makes sense. If it's below that, it's not going to give off any energy or any electrons. Number 2, okay? We can say that the higher the intensity of the So the brighter the light is, would be the higher the intensity of a minimal or of a threshold frequency. The more electrons are emitted. So that means if you shine more intense light on the metal, then there's more electrons that are sent out. So you can send out more and more electrons the more intense it gets. Okay? So you got to have the threshold frequency. If you don't, if it's not going to give off any light, the higher the intensity, the more electrons are given off. And the third thing is the higher, the greater the frequency above threshold frequency, the faster the electrons are that are emitted. Okay? So one, it needs so much frequency in which to emit electrons. Two, if you brighter intensity, that same threshold frequency, then you get more electrons off. And then if it's higher frequencies yet, kind of like putting in multiple dollars in a vending machine, you get more out. You're going to get faster electrons sent off. So that's what I'm going to end with. Now this is a 3-day assignment. Okay? So today is Tuesday. It is due on Friday. All right? And you'll need help at different parts because I didn't go through everything today. So this is what I want you to do between now and Friday when you're working on this. And you'll get some more information tomorrow. Okay? Tomorrow's Wednesday, so you'll get some more information tomorrow. This is what I want you to do. I want you to look at page 296. And I want you to do 1 through 5. Those are writing out answers, not calculations or anything. And then 299, 45 through 48 have to do with energy and frequency and wavelength equations, which I think most of you can do. And then 64 AB, we have not done anything with that yet. So this here you can probably do right now. This here you could probably do some of it with some reading. And then this one here we're going to do tomorrow. We'll look at tomorrow. 64 A and B. Okay? Okay. This is something that's a little different than normal. We're usually doing some calculations, do a little bit more work with that. But this is some reading I'd like you to really think about going through and reading through so you can get a real good grasp of what's being discussed here. It's not easy material. Then on Thursday we'll get into the quantum theory. And that's with your energy levels, your sublevels or subshells, which is S, P, D, and F. We get into where electrons are in certain levels, and then they can only hold so many electrons and so forth. And we'll get into that on Thursday. Okay? And that's your quantum numbers. We're going to start getting into quantum numbers and that. So, really good illustrations, really good descriptions of what we're doing. So we'll probably finish up this week just going over quantum numbers and working with those ideas on getting into Friday.